All right, let's take a look at problem 11, which looks like it's going to be a longer one. So bear with me. So we have a Carnot cycle that operates in a closed system using steam. Saturated liquid at 20 bar, state A is heated isothermally until it becomes saturated vapor. State B expanded by reversal process to 10 bar, state C, and then physically condensed to state or partially condensed to state D, and finally compressed by reversible adiabatic process to state A. And then in part A, they want us to calculate the physical properties, so using the steam tables for all of those states. So the first thing I'm going to do is I'm just going to draw a sketch of my Carnot cycle on a T versus S phase diagram. Okay, and so we're going to start with state A. Okay, and state A is going to go to state B. Okay, so this is going to be our isothermal step, in which we have some exchange of heat with our hot temperature reservoir. Okay, then we're going to go from B to C in an isentropic step. Then we go to C to D in another isothermal step, and in this case we're going to reject heat to our cool body reservoir. And then we're going to have our last isentropic step in which you go back from D to A, right, to complete the cycle. Alright, so the first thing I'm going to do is just collect physical properties. Then we're going to compute, looks like heat and work for all four legs, calculate the net amount of work, and then we'll compute efficiencies. Sounds like fun, right? Okay, and I'm going to try and go a little faster just because there is a lot to do here. So in state A, we're starting with a saturated liquid. With a pressure of 20 bars. Okay, so we have essentially a two-phase system, right? This corresponds to a liquid at saturation. So if I have a single component system at two-phase coexistence, I need just a single degree of freedom. I have one pressure, so my system is fully specified. So you might think to look at the saturated steam tables. I'm going to look at superheated just because I know those are sorted by pressure, and the first entry will correspond to the value at saturation. And so from that, following the problem, I'm going to get TA, I have P, then I need VA, UA, HA, and SA. Okay, so let's go ahead, go to our steam tables, superheated steam tables at 20 bar, and see what we have. So I'm already in the superheated steam tables. I'm going to find 20 bars. We're told we have a saturated liquid, so I'm going to write down my properties here of my saturated liquid, where this is my saturation temperature there. So 212.38. So I'm at 212.38. So I'm at 212.38 degrees C. So let's see, V is 0.00118. 0.00118. U's 906.27. Come on. In the interest of space, I'm not going to write down the units. We'll just write everything, or everything will be in the units of the steam tables. So it will be consistent throughout. 906.27. Come on. 0.27. HA 908.62. And SA 2.4470. And we have a saturated liquid, right? So I'm just going to make a note, right, that here we have a system with a quality of 0. Quality of 1 would correspond to saturated vapor. So QA is equal to 0. All right, so now in state B, it's going to be heated isothermally until it becomes a saturated vapor. Okay, so in B, okay, we have a saturated vapor. All right, and since A to B is an isothermal process, TB is equal to TA. So this is going to correspond to the corresponding vapor in equilibrium with the liquid in part A. All right, there would be at saturation with that state at A. So my temperature is, again, 212.38 degrees C. And, well, since it's going to be at saturation, I know that PB is going to be equal to PA. And that'll be equal to 20 bars. Okay, if I can get this to write correctly. That'll be 20 bar. And then let's go and let's read off all of our other properties that we're asked for. So we need VA, UA, HA, and SA. That would be B. Okay, and it's going to be this. Okay, so I'm just returning to my saturated or superheated steam tables, but now I need the vapor. So V is 0.0996. So 0.996. U is 2599.2. 2599.2. H is 2798.4. And S is 6.3392. All right, so that's in going from, so we have A and B. Then C, we have expanded by reversible process to 10 bar. Okay, so say C, state C, we're told is at a pressure of 10 bar. And we know we have an isentropic process and going from B to C. So I know that SC is going to be equal to SB. So if I go over to my superheated steam tables and I find 10 bars on here, I'm reading across my entropy column. Okay. And my entropy is, so SC is equal to SB. Let me write down its value. And that's equal to 0.63392. See that 6.3392 is between that of a liquid or vapor. So I must have a two-phase system. Okay, so let me make a note here that QB was 1, which is saturated vapor. So here I'm going to have a two-phase mixture. And so what I'll need to do is I'll need to write down entropy, volume, internal energy, and enthalpy of my liquid and vapor. And then once I have that, based on the known specific entropy of my system, I can calculate the quality. Then once I have my quality, I can calculate my property of interest. So say my specific volume of my system will be specific volume of liquid and vapor weighted by the fraction of the system that's liquid or vapor. Okay, so let's do it. So I have SL and SV. So let's do SL, SV, VL, VV, UL, UV, and HL and HV. and we were at 10 bars. We knew we were in between the two. Okay, so VL is 0.00113, 0.00113. Vapor is 0.1943, 0.1943. Bam. U 761.56. V 2582.8. H 762.68. Vapor phase 2777.1. Okay, then S 2.1384. Come on, stylus. 1384. Vapor 6.585. All right, so I'm going to work out an equation for the quality, calculate the quality in C, and then from that we can calculate V, U, and H for my system. Oh, and let me note, I have two-phase coexistence, so I know T. My temperature is 179.89. Okay, 179.89 degrees C. So let's calculate our quality. So as a reminder of how to calculate my quality, okay, the idea is that the extensive entropy of my system, right, in state C, is a sum of, so I'll write this as ml, so this is the mass, total mass. ml is the mass of my liquid phase times the entropy of my liquid plus mass of my vapor times the specific entropy of my vapor phase. So this is my total extensive entropy. This is the extensive entropy of my liquid and extensive entropy of my vapor. They're extensive properties, so they're additive. Okay. Then what I do next is I divide through by m. So I get SC is equal to ml over m times SL, and then mv over msv. Okay. Remember, m, my mass, is equal to mv plus ml. So ml over m is the fraction that's liquid. mv over m is the fraction by mass that's vapor. Okay. We define the fraction that's vapor as the quality. So Q is equal to mv over m, and then we get that 1 minus Q is equal to ml over m. Okay, so plugging that in, I get that 1 minus Q times SL plus Q times SV. So next, we'll just solve for Q. Okay, so distributing SL minus Q SL plus Q SV. So I have SL plus Q times SV minus SL. Therefore, I get that Q is equal to SC minus SL divided by SV minus SL. All right, and this would be QFA C. And then once I have Q, all right, VC would just be 1 minus Q times VL plus Q VC. UC would be 1 minus Q UL plus Q times UV. And finally, we would get, and I'll just summarize them, we would get that HC would be 1 minus Q H liquid plus Q times H vapor. Alright, so I'll jump over to MATLAB. I'll compute them all, and then I'll summarize them here. So TC, PC, you already have, but then VC, UC, HC, and SC, which you already have as well, and just to make it complete, let's get Q. Alright, so let's go ahead and compute. So I'm going to need to, jump over to MATLAB. Okay. Let me just clear everything off from the last problem. Okay, so let's have, SL and SV. VL VV let's get UL and UV and HL and HV and then we'll need SC so we can calculate QC. So SC is 0.63392. So you get the QC, and let me make a note up here. So let's just say state C. So then QC is SC minus SL divided by SV minus SL. Then once we have Q, we have that VC is equal to 1 minus QC times VL plus QC times VV. HC is equal to 1 minus QC times HL plus QC times HV, and UC is equal to 1 minus QC times UL plus QC times UV. Phew. Okay, so summarizing everything. T was 179.89. 179.89. Come on. Degree C. Pressure was 10 bar. And so now we get VC's negative, which isn't right. So so QC, I end up negative. So I have an issue with my QC calculation. And let's see what it is. Let's see if I've got my SL and SV values right. SL 2.1384, SV 6.585, and then SC is equal to SB is 0.633, 0.633. Oh, there's my answer or problem. All right, I goofed this up. So SB is 6.3392. So 6.3392. So trying again. Now I get a Q that's less than 1. And now everything looks like it makes sense. So QC is 0.9447. So it's a two-phase mixture. VC is 0.1836. UC is 2,482. HC's 2,665.7. And then SC, again, is what we started with, that 6.3392. All right. State D. So for our last leg, okay, and going from C to D, we know that we have an isothermal process. So it tells me that TC, or TD, is equal to TC, and that's going to be equal to our 179.89 degrees C. Okay. We know that going from D to A, we have an isentropic process. So it tells me that SD is going to be equal to SA, and that'll be equal to 2.4470. Okay, and from the problem statement, it says that it's going from C to D, our system's partially condensed. All right, so what I expect then is that here we have a two-phase mixture that's mostly vapor. That here we're still going to be, we're at the same temperature. That we're going to have a two-phase mixture. It's just QD is going to be less than QC. So how can we check that out? Well, we know our entropy is 2.4470. So at 10, some superheated steam tables at 10 bar, I see that my S is between that of my saturated liquid and that of my saturated vapor. So again, I must have a two-phase system. Okay. So in terms of calculating QC, or Q, which in this case would be QD, and then VC, UC, HC, the calculations are going to be exactly the same as the last problem. And since we're at the same temperature, okay, we have a saturated system at the same temperature. Okay, so I'm still here at 10 bar. My entropy is between that of my liquid and vapor still, so I'm still a two-phase mixture. So the calculation is going to be exactly the same. So what I'm going to do is I'm going to copy this block, because now if I'm at state D, all that changes is SD is now 2.4470. And then this is going to become QD. And this will be SD minus SL divided by SV minus SL. I'm going to calculate VD, HD, and UD. And I just need to change, instead of using QC, to use QD. Okay, so it's two-phase mixture at the same temperature, right? And so it's all of these properties, right, are the same. All those properties at saturation. All right, so now I have a quality which is a lot smaller, okay, much closer to 0. So we end up getting QD. Okay, so we're still two-phase. Okay, so let me just make a note. We're still two-phase. Okay, only now QD is 0.0694. So while here our quality put us, very close to saturated liquid, now we're very close to saturated liquid. So QC, we're very close to saturated vapor, very close to quality of 1. So very close to saturated vapor. Now we have a quality close to 0, so we're close to that saturated liquid region. Okay. So QD, and then let's get everything. So VD is 0.0145. Okay. And all of my units are the same as the steam tables. I just skipped them for convenience. Okay. So this doesn't get too crowded and too messy. It'd be a lot easier right, if I was writing on a piece of paper. So HD was 902. Come on. Come on. So HD. It's this new stylus. HD 902.4834. And UD is 887. 0.9565. All right. So we calculated all of our properties at all of our states. All right. So we've got that. We're going from saturated liquid to saturated vapor, two-phase mixture that's mostly vapor, to a two-phase mixture which is mostly liquid. Okay. And then back to A. So we've got all of our properties at states A, B, C, and D. And now they want to know the amounts of heat and work involved in each of the 4 legs. Let's do it. So let's start at the beginning. So let's start with A to B. And I'll work out the formulas, and then we can go to MATLAB, compute everything, and tabulate them. Okay, and so my 2 isothermal processes, A to B and D to C, is I know where I have heat exchange. And then there's going to be work exchange in all the steps. Okay, so from A to B, we have an isothermal process. And we're told, so state A to B, so all we're told is that we're heated isothermally until it becomes a saturated vapor. Okay. So A, we're just told that we have isothermal heating. From B to C, so we know it's isentropic, and we're also told that it's reversible. And then C to D, we have an isentropic process. Or C to D, we have another. So A to B is isothermal, B to C is isentropic, C to D is isothermal, D to A is isentropic. This is our Carnot cycle. All right, so we have a reversible cycle. Okay. All right, so it's a Carnot cycle, so we have a reversible cycle. All right, so we have a Carnot cycle, we have a reversible cycle. All right, so I'm going from A to B. Okay, what I'm going to use then is, so we have an isothermal process. Okay, and it's a Carnot cycle, so we're assuming that this entire process is reversible. So with that in mind, okay, I know that ds is equal to dq reversible over t. So dq reversible is going to be equal to TDS. Okay, so by Q reversible here, this could be a reversible heat exchange and going from A to B. T's constant, so this could be T integral from A to B ds, which becomes T times SB minus SA. Okay, so I know that QAB is just going to be T times SB minus SA, which is great because I have SB and I have SA. Okay, so that's Q. Well, what about W? Well, first law of balance, delta U is equal to Q plus W. So therefore, come on, pen. Therefore, W is going to be equal to delta U minus Q. I'm writing it out formally for this process. W from A to B is going to be equal to delta U will be UB minus UA minus Q will be a minus T SB minus SA. Bam. Okay, so there's state A to B. Let's add a new page. A new page after. Okay, I'm going to work out all the equations, and then I'll calculate them, and we'll tabulate all of these differences. Okay, and yeah, let's do it. So now let's go to B to C. Okay, so B to C we know is isentropic. So it's isentropic. And again, we're told it's, expanded reversibly. Okay, so it's isentropic, and we're told that it's expanded reversibly. So if I think back to the first problem, all right, so for my reversible process, I know that ds is equal to dq reversible over t. Okay, but it's isentropic, so ds is 0. So since ds is 0, right, it must be that q reversible is 0. Okay, so therefore we get that q from B to C is equal to 0. So then to get W, I go to my first law of balance. So delta U is equal to Q plus W. Q is 0. So we're left with W for B to C is equal to delta U, which in this case will be UC minus UB. All right, B to C. Now let's go C to D. C to D. Okay. We have another isothermal process, and we're told C to D. We're just told that it's partially condensed to state D. Okay. So we have an isothermal process and going from C to D, in which we partially condense our system. And again, right, it's a Carnot cycle. So in our Carnot cycle, we're assuming that we have a reversible process. Okay, Carnot is our idealized cycle. So it's isothermal. So our analysis is going to be identical to A to B. So I start with ds, I know is dq reversible. This is my reversible heat exchange over T. Okay, so therefore, we have that dq reversible is equal to TdS. So my reversible heat exchange, which for this case would be the heat exchange in going from C to D, would be equal to, so it's isothermal, temperature is constant, so this could be T times the integral from C to D of ds. Okay. As a note, as I come up here, remember T is the same in state A and B, so you could write down either T. So let me just write down, say, TA. Okay, because I'm going to have the same thing down here. Okay, is integral of TdS, which is going to be equal to, so temperature at C and D are the same, so I'll just write Tc times SD minus SC. All right, so I get that Q in going from C to D is just equal to my temperature at C times SD minus SC. Okay, box that in. How do I get W? First law of balance. Delta U is equal to Q plus W. So therefore, W is equal to delta U minus Q. Or, so here we get the W in going from C to D is equal to UD minus UC minus TC SD minus SC. Whew. And as a note, so something that's interesting here is in Q, okay, we're going from, well, do I have, no, actually I don't have it. It's in my first step from A to B. It's only from A to B. I take it back. From A to B, we're going from saturated liquid to saturated vapor. So that's equal to the entropy of vaporization. So my saturation temperature times my entropy of vaporization is equal to my enthalpy of vaporization, right? So that's kind of cool, right? And so T times this would be equivalent to enthalpy of vaporization again, and this would be my internal energy of vaporization. Down here, it's two-phase, so it's not quite the same. All right, so I've got Q, then I've got W, right? All is looking good. So I have A to B, B to C, C to D. Then is that it? Oh, then I need D to A. Okay, so I need D to A, which is my last isentropic step. Okay, so again, Carnot cycle, we're assuming our process is reversible. All right, so ds is equal to dq reversible over T. Change in entropy is 0, it's isentropic. So Q reversible, or dq reversible, must also be 0. So we end up with Q from D to A is 0. Okay, and then to get W, we go to our first law of balance. So delta U is equal to Q plus W. So Q is 0. So we're left with W from D to A is equal to UD minus UA. All right. So let me set up a table. We'll summarize our results, and then we'll go over to MATLAB and compute. Okay, and so what I'm going to tabulate is, let's tabulate our work and our heat. And we'll have A goes to B, B goes to C, C goes to D, and D goes to A. Okay, and we'll summarize our work and heat. Now, we haven't played around with units. They're all going to be the same as the units of energy used in the steam table, so kilojoules per kilogram. All right, and now in all these calculations, I'll need temperatures, entropies, and internal energies. So let's try and summarize everything. So I have state C. I don't have the temperature of state C, so let me get temperature. And I need to make sure I'm using Kelvin for my unit of temperature. So TC is 179.89, and I'm going to add to it 273.15. Get my temperature in Kelvin. And so TC I needed. TD is exactly the same. And so let me get, so TD. So TD is just equal to TC. Let's get state A. Okay, and in state A, I'll take a shortcut, if you will, because in my calculation it looks like I only need U and S. So let me get TA is 212.38, and I'm going to convert to Kelvin. It's my temperature. UA 906.27, and SA is equal to 2.4470. State B, TB is just equal to TA, and then UB is 0.0996, and SB 6.3392. All right. So let's get QAB is equal to TA times SB minus SA. WAB is equal to UB minus UA and minus, let's get QAB I'll use since I just computed it. QBC is 0. WBC is equal to UC minus UB. QCD is equal to TC times SC minus SD. SD minus SC. WCD is equal to UD minus UC minus QCD. Oh. And WDA is equal to UA minus UD, right? Yeah, I wrote this backwards because this is my initial to my final state. This should be final minus initial. So that should be UA minus UD. Let's see what we've got. Okay, so QAB is 1,889.8. Okay, that's good. It's positive. It's heat coming from my hot body to my cool body. WAB is negative 2,000 796. Okay, WBC 2482. QCD, another one, negative 1763.3. Negative 1763.3. CD is 169.1536. And WDA 18.3135. All right, now the first thing I want to do is I want to check to make sure my answer makes sense, right, or that it checks out. And how I'm going to check that it works out is, so we have a cycle, right? We're starting and ending at the same state. So the internal energy of my starting state is equivalent to the internal energy at my ending state. Okay, so again, if we do a first law balance on our cycle, right, my first law balance is delta U is equal to Q plus W, right? And since I'm starting and ending at my same initial state, delta U has to be equal to 0. Okay, so Q and W are going to be the sum of, it's going to be the net Q and net W, the sum of all my Q's and all my W's. So what I want to do is I'm going to sum up my W's here, I'm going to sum up my Q's, and make sure that those two sum to 0. Okay, so here's hoping. Okay, so Q, would be QAB plus QCD. W is going to be equal to WAB plus WBC plus WCD plus WDA. Woohoo! It's a miracle, right? So they work. So I did something right. So W I get is negative 126.4576. And then Q is exactly the same, 126.4576. All right, so this first and foremost is awesome because this means my calculation checks out and it's consistent. All right, and I get the correct result that the net effect is heat's added to my system, and then my system does work on the surroundings. So I add heat to produce work. Now we'll go back and look at the questions in a second, but I want to try and connect, right? What is all this in terms of our picture of our Carnot cycle? So the picture we have of our Carnot cycle is that we have some hot reservoir, or some reservoir at a hot temperature, which is going to deliver heat to my system. Okay, I'm going to extract work from my system. Okay, and then I'm going to end up. All right, so heat's added to my system, I remove work, and then I'm going to need to end up delivering heat from my system to some cold body reservoir. Okay, so in terms of making connection, so TH, okay, I got to go all the way up to the top. This corresponds to this isothermal process from A to B. Okay, so TH you could think of as TA or TB, which is the same. Okay, so this is essentially TA, and I'll go to MATLAB since I think it might be easier there. TA is 212.38. This is my 212.38 degrees C. Okay. Now QH right, that's going to be then the heat, this positive heat added to my system at state A to B, this 1889.8. So this is my QAB, 1889.8. Yep. Okay, cool. Okay, the heat that's being, or the work that's being extracted from my system, so my work's doing system on the surroundings. That's my network here. It's negative because my system is doing work on the surroundings. Since I have this directional arrow, which is showing it coming out, I'll write it as positive just so it makes sense. But that's 126.4576. All right, so my work, and I can even label as work out, is 126 point. So the net work delivered 126.4576. Okay, both these are kilojoules per kilogram. Okay, heat's being removed from my system and delivered to that cold body. I already have the directional arrow out, so that's 1763.3. My cold body, that corresponds to state C to D, that isothermal process. So I can use TC or TD, they're the same, but that's 179.89 degrees C. Bam. All right, and already I see that my process is pretty inefficient, right? Why do I say pretty inefficient? All right, is, make the connection, first law, industrial revolution, the steam engine. All right, my goal is to take heat and convert it to work. So the required heat that I'm adding to my process is 1889.8 kilojoules. And of that total heat I'm supplying, I'm only able to extract 126.4576 kilojoules per kilogram of work out. So the amount of energy I'm supplying to my system that I'm pulling out as mechanical work is really small. All right, so it's really inefficient. And part of that is when you look at my temperature of my hot body and my cooler body, that they're pretty close to each other, right? So cool. So that's schematically, when I try and connect it to my picture of Carnot, that's what I have. All right, the picture of our cycle on our T versus S phase diagram. All right, that's what we use for analysis and performing our calculations around. C, what's the net amount of work that's produced? Oh, that's just summing up our work column. So we already did C, right? So we just summed up this. This is the net work, and so it's negative. So it's net work that our system is doing on the surroundings. And then D, calculate the ratio of the net work over the amount of heat absorbed at the high temperature of the cycle. How does this value compare to the theoretical efficiency of the Carnot cycle that is calculated based on the two operating temperatures? All right, so what they want us to compare is, again, this should work out because if we just completed our sanity check, that our first law is satisfied for our cycle. All right, in this case, that Q is equal to negative W. But they also want us to do a check using our equations for the efficiency of a Carnot engine. Okay. Whoop. So in general, all right, when I think about efficiency, and so I'll call it efficiency Carnot. All right, I describe efficiency as desired output, which in this case is the work that I'm able to achieve. Right, desired output is the mechanical work that my system's doing, divided by required input, which in this case is QH, right, the heat that's being added from my hot body. Okay, now in terms of signs, okay, my system is doing work, so I know work will be negative. Okay, heat's being added to my system to the hot reservoir, so Q will be positive. All right, and so we typically write this as negative W, so it's a negative net work because my goal is for my system to do work, so that's negative, and I'm adding heat, QH. And so I'm going to rewrite this as negative W, which is the net work we just computed. Then QH, right, just for completeness, is the heat added in our process and going from A to B. Okay. Now, for our Carnot cycle, okay, as shown in the book, you can show that that is equivalent to 1 minus TL over TH. Okay, the ratio 1 minus the ratio of my cold body over my hot body. Okay, and remember it has to be your cold body over your hot body because TH is greater than TL, so this will be less than 1, so that I get a fraction between 0 and 1. Okay, the greater the temperature difference, the greater the efficiency. The smaller the temperature difference, the smaller the efficiency. So let's go ahead and compute these. Okay, and here note that we need to use absolute units. And if you want to derive this equation, you actually could based on what we have, because you have all of our work terms, right? You could add up all of our work terms, and if we have a second, we can do it, right? You just add up your work terms: WAB, WBC, WCD, WCD, and then WDA. You could add up all the work terms, and then you could, you have QH, right, and it should work out, right? You should be able to get to this final place. But anyways, here we go. So Carnot. So let me call this efficiency actual. So we said negative W divided by QH, which is QAB. And our efficiency due to temperatures is 1 minus TL. We were labeling that, so temperature C and D. So we'll just do TC divided by TA. And they both are exactly the same. Woohoo! Both are 0.0669. 0.0669. Okay, so both give us exactly the same answer. Yahoo! All right, so I am going to stop at that. Right, the efficiency is pretty low, right, because the temperature difference is the same. So I'm going to stop recording here, and let me see if I can make a part 2 to continue, where we could try and add up all the W's and Q's, and see if we can, check this equation that way. Hope that helps. Let me know if you have any questions. All right, so I'm just following up from our last problem. I just want to make it up in 2 parts in case you don't want to watch me that long. I'm just going to see if, based on all the expressions we have, if we can obtain this Carnot efficiency using temperatures. Okay, so all I'm going to do is I'm going to write everything out. Okay, so W, okay, is going to be equal to W AB plus W BC plus W CD plus W DA. Okay, so that'll be equal to, okay, WAB is UB minus UA minus TA SB minus SA. So we have UB minus UA minus TA SB minus SA, and that just as well could have been TB. BC is UC minus UB. So it is plus UC minus UB. CD UD minus UC minus TC SD minus SC. So we have plus UD minus UC minus TC SD minus SC, and then D to A. D to A is UA minus UD. Let's see if I can fit it in. Plus UA plus UA minus, come on, please, UD. All right, so let's cancel terms. So let me switch to red. Here is plus UB. Here is minus UB. Here is minus UA. Here's plus UA. Here's a plus UC, a minus UC, plus UD, minus UD. And that might be everything. So we get the W. Okay, W net is negative TA SB minus SA minus TC SD minus SC. All right, now let's see. So we need Q over, or W over QH. So let's get QH. So QH is what? QH is QAB, which is TA SB minus SA. So QH is TA times SB minus SA. All right, now so let's see. So then my efficiency, okay, I'm going to define as negative W over QH. So negative W TA SB minus SA plus TC SD minus SC divided by TA, and that's SB minus SA. Cool. All right, so now, okay, what I need to do is if I look at my Carnot cycle, okay, isothermal step, isothermal step, isentropic step, isentropic step, okay. We have a cycle, so if I start at A, I end at A, okay. So if D and A are both isentropic steps, so delta S is 0, okay, and the sum of my delta S's as I go around this cycle is equal to 0, okay, it must be that this entropy change is equal to that entropy change, okay. So again, okay, so before we go back up here, okay, it must be that delta S, okay, is equal to 0, where that's going to be equal to delta S, that's going to be equal to delta S, and going from A to B, plus delta S, and going from B to C, plus delta S, and going from C to D, plus delta S, and going from D to A. Okay, so BC and DA are both my isentropic steps, so therefore we get the delta S AB. So the change in entropy in going from A to B has to be equal to the negative change in entropy in going from C to D. Okay, cool. Okay, so how does it help us here? So let me add a new page. Okay, so SD, okay, I'm going to rewrite it as SC minus SD. Okay, or equivalently, I could just plug in directly, right? Because SD minus SC is going to be negative SB minus SA. So what I get then is eta is equal to TA SB minus SA, and then negative here, so I change the sign, minus TC divided by, okay, QH, which is TA SB minus SA. So I cancel all these SB minus SAs, and I'm left with eta is equal to TA over T1 minus TC over TA, okay, where TC is the temperature of my cold body, TA is the temperature of my hot body. All right, so there, based on all my equations, right, we get it, it checks out, I get 1 minus TL over TH. So what a big, long, fun problem. Hope that helps.